All right. Well, thank you for the opportunity of speaking. I feel a little bit of an interloper in terms of this being very heavily quantum mechanical. But what we've been interested in now for a few years is actually trying to understand the optoelectronic properties of organic semiconductors. And so really what we're looking at is the morphology of these films at an atomic level. And another way of that I could put it is really trying to understand the optical properties of these materials, and particularly the difference between solution processed and vacuum deposited light emitting diodes on organic photovoltaics. Now, what I'll do is primarily give you an overview of the things that we've been looking at and the types of questions which are becoming accessible, for which there is a big call for also doing more detailed calculations. Now, if we really think about, what's actually happening, there's really a revolution in organic semiconductors at the moment. I mean, we're going from rigid, stiff, monocrystalline silica solar panels to where we can have high efficiency polymer-based materials which are flexible, going from the inorganic LEDs to organic LEDs, which can be not only very high efficiency, but flexible, can even be sprayed onto materials. And one of the areas which I'm most interested in myself is also when we can go to full electronic devices, which could be on a polymer substrate. And there is just so much scope in terms of the organic chemistry, in terms of modifying these materials, that there's just the future seems very bright for them. And I mean, if we're thinking about career, of course, OLED displays are a major product. But if we're thinking also about, just where this is heading in the future, I mean, Heliotech in Germany can do vacuum roll-to-roll production of organic photovoltaics. And the question with all of these things, the questions that we've been addressing is trying to understand how these devices or how the morphology leads to different efficiencies in their optical properties. So Heliotech's materials can easily get to 13. I think they're up around about 16% efficiency now, but their production efficiencies are a little bit lower. But still, considering that you can do these roll-to-roll and they're lightweight and flexible, they're really becoming a major competitor to silicon devices. So actually, if I think about the way that we actually got into this, we were collaborating with a number of people developing these materials and doing very high-level calculations on them. And I was thinking about embedding, they were using molecular dynamics in order to get an idea of the local embedding of some of the emitter molecules. But the questions that they'd like to answer that they really couldn't answer with the ways that they were approaching it was things like the mechanism of electron and hole transport, the mechanism of device failure, and the effects on manufacturing of device efficiency. And one of the real sticking points in this whole field is that a lot of the materials, if we think about the sort of flexible phone screens that we have today, OLED screens, these are actually built by vacuum deposition. Whereas what we'd really like to be able to do is to get the same efficiency devices if we were using something like an inkjet printer to actually deposit the materials instead. And how do we actually relate and understand these differences in morphology to the differences in the optical properties? So if we just go back just to give a little bit of a background, so we think about the structure of an OLED. The part that we're mostly focused on is an emission layer. It's got a cathode at the top, electron transport layer, and underneath it, it's got a hole transport layer and anode, and these are on a substrate. These devices are incredibly thin. So they're on the order of 150 to 100 nanometers often. And it's this emission layer which is the most critical for defining the nature of the properties. So the particular one that we actually started with back in 2017 was a green emitter, ERPI-ACAC, inside a host substrate, which is CVP. And the interesting thing about this material is that it can both be processed from solution and also from vacuum. The more modern materials really can only be processed from solution. And so just to give you a little bit of an idea about why that we actually have differences. So if we take just the substrate material, if we deposit it under vacuum or evaporate it from chloroform, if superficially there's really no difference between the two materials. However, as these materials age, the solvent one can develop cracks, indicating that it doesn't age in a uniform manner. And you can also see that things like the grain size are different. So even on what is a relatively simple molecule, there are differences in the microscopic morphology of these materials, and these do affect the properties that you actually see. So the first question that we actually looked at was that actually, why is there an efficiency maxima at around 5 weight% of the emitter in many of these types of, I mean, of course, it's not necessarily 5 weight%, but in the case of ERPI, it's 5 weight%, and it's in the order of, I mean, a similar that value for many of the other materials. And so a lot of the previous work on trying to understand these had been done by people simply just making up the morphology and then performing, as I say, high-level calculations on a particular morphology. But we thought that we could do better, and really compared to the assembly of biological molecules, which I've been involved in for a long time, these are relatively simple. And so the way that we proceeded with this is to create molecules in a vacuum and then to simply mimic the process by which these layers are experimentally created. And so what we simply do is to create molecules in space, allow these to drift and bind to the surface spontaneously, and we can now do this relatively simply and generate layers of 50 to 100 nanometers with the types of resources that we have available. Now, once we have this, we can then go back and compare the properties of these layers or these morphologies to experiment. Now, just before I go on to what we can actually calculate with this, I would point out that these are very, they require accurate force fields. You need force fields for a whole range of molecules. This wouldn't be possible without the other part of my group, which focuses on the development of empirical force fields for a whole range of arbitrary molecules. This is wrapped up in a web-based server, which we call the ATB, not a very creative name. But this allows people from the community to submit molecules. We perform a series of quantum mechanical calculations in order to be able to fit parameters. And as of today, we had around 6,000 registered users, and we have a database of over 590,000 molecules. Most of these are molecules of interest in drug design, but a lot also of interest in materials design. So if we actually begin to go back, because as I say, that before a lot of this work, the focus was on the exact interaction of particular pairs of molecules to try and understand where this efficiency came from. And what we were able to show instead is that if we took a very crude model of the way that that excitons and holes and electrons could actually jump through these materials, and looked to see at what point that we find percolating networks and whether these networks terminate, because you can you would be able to actually, I might just put on my laser pointer. And so in these systems, we're actually injecting electrons from one layer and holes from another layer. These come together and form an exciton. and then that exciton ends up on one of the emitters, and then it will actually fluoresce. Now, if we want to get high efficiency, we need a high number of emitters. We need a high number for where the exciton can end on an emitter, but not progress a hole or the electrons we don't want to progress throughout the entire layer. And so what we can see is that if we're at 28%, most of the molecules are effectively isolated. Once we get to 5% we find we have extended networks through this material, but which will still terminate. Whereas if we go up to something like 14%, we find many pathways which simply go from one side of the layer to the other side of the layer and effectively short circuit the device. And so just with such a simple principle, we could then directly predict what would be the highest efficiency ratios for these materials, and they came out very close to the experimental efficiency. Now, once we actually did that, we could consider moving on to look at other properties. You know, for example, I mean, how we actually get through holes to actually merge from or to come from the electrodes and actually migrate into the active layer. This is one of the factors of device failure, so that if we need some intercalation of these two materials in order to get high efficiency, but once the materials again begin to diffuse right through each other, then again the device will actually fail. And this is one of the reasons for heat failure of OLED devices. But the thing that I thought I would discuss it a little bit more detail just a moment is really one of the questions which had puzzled people for a long time, and that was trying to understand basically the way that the different deposition techniques related to device efficiency. So if we actually have two, and these are two closely related emitters, ERPI and ERPI-ACAC, and in the case of this particular emitter, the asymmetric emitters have a higher efficiency. And so, and it may not seem like much, but this is actually a very significant increase in the efficiency for these particular devices. And so we were interested in looking at whether we would be able to predict why one was more efficient than the other. And if we think about one of the reasons why we can gain efficiency on an orientated molecule is that what we would really like is to have that the transition dipole moments sitting parallel to the substrates, and so the light emission is perpendicular to the substrate and more of it leaves the material. If they're randomly oriented, then we're going to have less light being emitted. Now, if we actually think about, and there is certainly a wide range of experimental data which has got where you can actually look at the wavelength dependence and look at the viewing angle to determine which way the light will actually come out from these materials. Now, in the case of ERPI and ERPI-ACAC, and if we're looking at the average orientation of the light or the dipoles of the molecules, that what we can see in the case of ERPI-ACAC is that there is an increase in the net alignment, which actually allows for greater light emission. Now, what you can also see in the case of the ERPI, it's a symmetric molecule. And so we have the light coming out in multiple different directions. And so simply aligning it along one plane does not necessarily gain you an advantage because of the alignments of the other potential transition dipole moments. So if we actually simulate and deposit these materials onto a graphene substrate with the same host materials, so both of these with CVP, that we do actually see a difference in the orientation between these two molecules. We can predict this. And so what you're actually seeing here is then, so it's basically a plot of the sine of the angle. And so if it was purely anisotropic, this would be a flat line across the entire range. Now, the anisotropy in this case is actually introduced by the vacuum interface. It's actually interesting with this material, it's either solution deposited, the actual alignment is opposite to what it is in vacuum. And so when we actually deposit these, the ACAC group has a slight tendency to project up while the layer, before the layer basically solidifies, or it enters a glassy transition. And as this is depositing, it gives a slight increase in the orientation. Now, the question that we also have to know in order to be able to calculate what will be the overall efficiency of the molecule is what is the transition dipole. This is still debated for these materials. And so what we compared was two basically extreme cases. One where we considered the transition dipole to go directly along the carbon-nitrogen bond, as what we would see here, and also results which had been published by two different people related to both ERPI and ERPI-ACAC, trying to get a more accurate prediction of these transition dipoles. The interesting thing when we actually did this, and we looked at it, so if we actually take the a very simplistic, naive way of treating the transition dipoles, and we look at the orientation of these materials, we actually get not a bad prediction between the difference in the orientation, the expected efficiency of these two materials. If we actually take the transition dipoles calculated otherwise, it actually doesn't matter how much orientation that you get. It's actually very difficult to reproduce the experimental differences between these two molecules. And that's partially because, and you can see it reasonably easily here, because in the ERPI, these are basically partially orthogonal, that as we align one, the other ones are out of alignment. If we can manage to get a perfect alignment in the plane, we can get an increase in efficiency of, in the case of ERPI-ACAC, in the case of actually taking the two calculated values, that because then in the case the ERPI-ACAC is non-planar and the ERPI is in line, that actually the difference between these two is much smaller, even though the molecule is itself aligned. And so at least just in terms of the morphologies, we would believe that these are a more realistic representation of the actual transition dipole moment of the molecule. Now, there's a whole range. I mean, once we could see that we could look at some of these properties, we moved on to look at a range of other related properties. And so one of them was to actually look at a series of low donor content organic photovoltaic materials. And so the question that we were really trying to address is why in many of these small molecule bulk heterojunctions is the optimal efficiency found at very low donor concentrations. And so it's really how are these donor and acceptor molecules aligning or combining in these materials. So again, we took a very similar approach, and this was published back in 2018. And that's a little bit lousy. I'm sorry, I just can't, oh, well, unable to change or to play the movie in this particular case. But look, we could look at a whole series of neat C60 films. We could also look at it with different concentrations of TAPC as our dopant in this particular case. If I really go to the short of it, basically what we were looking at is to see what fraction of donors could produce a pathway to the anode in these particular materials. Again, it turns out just by chance, it's around about 5%. And if we actually then think about that, if we're looking at the transfer of excitons through these materials, is that once we've got to about 5 to 8% of these materials, the entire material is about 73% connected. So if we only allow hopping of around about 1 nanometer between the TAPC molecules, that is as good as having a material completely doped. So if we're thinking about what is a realistic photovoltaic bulk heterojunction, these are often represented as really gross domains of the material within the matrix. We feel that the ones on the left here are far more realistic, where the material is actually spread reasonably randomly through the matrix, but because that excitons can actually jump in between, or electrons and holes can jump in between, this actually allows you to get a complete percolation through the materials. Now, we can actually look at this from the other side and actually look at the charge transport and luminance efficiency. So we were just looking at photovoltaic systems, then we could actually look at the opposite process, and that's actually charge transport leading to the release of light. And in this case, so this is actually a TC-TA mixture with the same emitter we looked at before, which is an ERPI blend. And experimentally, you could look at the effect of the guest concentration as a function of the quantum efficiency of this device. And you can see that it comes out at around about 10% as a maximum efficiency. When we're actually looking at the networks and pathways that we get for these materials, what you can see is that as we increase the 8%, we get many more emitters, which is good for efficiency. Once we go past about 10%, what we're actually seeing is the pathways connect right the way through to the anode. And again, we short circuit the device as opposed to actually allow emission. So finally, if we go to the next stage and look at the effect of manufacturing on device efficiency, can we do anything in terms of solution work? And so this is what we've been focusing on over the last year and a bit, and really to simulate evaporation of these materials from first principles. So literally to make up a solution at a realistic concentration and simulate the process of solution processing. So look, our first system was already very large. It was running to about 2 million atoms. So several 100,000 chloroform molecules that we had to evaporate. And what you actually see from here, and it's not that unexpected, but you'll actually see these films grow from the surface layer and progressively, and actually behind the surface layer, the material is almost unaffected by the growing film. Now, this is vastly different to the sorts of morphologies which have been widely used in calculations of the optical properties of these materials. Many of these had been generated under periodic conditions where you would simply remove the solvent at random. Now, this leads to spinodal decomposition, but at all the simulations that we've run would all show the formation of a film as opposed to there being an even distribution. And you could actually ask, why does this become important? And so one of the things that we could actually consider looking at, and we've been looking at in more detail, is mixed emitter OLEDs. So basically, we would like to produce a mixture of OLEDs and predict it to be able to produce white light. But we have a problem that will get spontaneous transfer from blue emitters to red emitters if they're close enough. And so we have to consider what ratios these have to be embedded in the materials. Also, how the materials are distributed within the layer during the deposition will also affect, of course, local concentrations will lead to differences in the color that we expect to get out even for the same material. And so this is just one illustration from the runs that we showed you before, and that you can actually see that while there is still solvent present, we find a high proportion of dimer formation. As we deplete the solvent, these dimers then dissociate again. And so as we're getting different drying rates, we're actually seeing different optoelectronic properties from these materials that we can actually predict. We can predict how much solvent will remain under long timescales. We could also predict the opposite process and things like what would happen to these materials if exposed to water or oxygen, and what types of traps could actually be formed in these morphologies. Now, the final thing that I just wanted to mention is that we can also keep going further into this, and we can actually look at the different processes of light generation and quenching, which can go on. And we can actually use kinetic Monte Carlo simulations, but not based on simplified representations of these systems, but on actual atomically validated morphologies. And then from this, predicts things like exciton density. So we could actually, predict how the excitons can actually move through, and how they quench and other aspects of it. So look, the atomic simulations are really providing unique insight in organic semiconductors. They can reproduce interfacial effects. Once we have these morphologies, you can calculate a whole range of properties. I've only highlighted just a few of the ones that we're looking at. And it also allows us to be able to test analytical models and help to interpret experiment. So with that,